In this question, we want to find n moments using column analogy method. We are given a beam with fixed ends A and B with a right angle triangular load with maximum value at end A of W kilonewton per meter. The length of the beam is L and E and I for the beam are constant. And here note that because both the ends of this beam are fixed, the end moments for this beam will be same as fixed end moments. To solve this using column analogy method, the first step is to draw the corresponding statically determinate beam, and we can get that by replacing fixed supports at A and B by pin supports. So my corresponding statically determinate beam will be corresponding simply supported beam. Now because this is statically determinate structure, we can draw bending moment diagram just by using equations of equilibrium. So first I will find support reactions by considering free body diagram of entire beam, and because we only have vertical loads, the pin supports at A and B will have one reaction each, and that will be reaction in vertical direction. So let me show. Reaction at A will be RA in vertically upward direction. Reaction at B will be RB in vertically upward direction. Now I can write equations of equilibrium. Sigma Fy equals to 0. This will give me RA plus RB because both are in upward direction and the applied load is downward direction. So minus, and the magnitude of this triangular load will be area of the triangle. So that is half height into base equals to 0. So this gives me RA plus RB equals to WL by 2. Let's call this 1. Next I will write moment equation about point A. So sigma m about A equals to 0, and I will take clockwise moment as positive. So this gives me the moment because of RA will be 0 because RA passes through point A. The moment because of distributed load will be clockwise. The resultant force because of this triangular load will be of magnitude WL by 2, and this distance will be 1/3 of the base length, that is L by 3, and the moment because of this will be clockwise. So plus force into lever arm. Next moment because of RB will be anti-clockwise, so minus RB into, and the lever arm for RB will be L, so that is L equals to 0. This gives me RB equals to WL by 6, and I can put this RB in 1 and get RA equals to WL by 3. So my RA is WL by 3 and RB is WL by 6. Now to find bending moment at any section at a distance x from end A, I'll take a section, say x at a distance x from point A, and it will be convenient to draw the free body diagram of part to the right of section XX. So this will be our segment. There will be reaction RB, this will be end B, there will be a smaller triangular load, and this distance will be L minus X because this distance is X and the total distance is L, so the remaining distance will be L minus X. So here we need to find this height, let's call this Wx. This we can find by considering similar triangles in this diagram. One triangle will be small triangle and another one will be the full big triangle. So for big triangle we'll consider this height divided by this base, and for the small triangle we'll consider this height divided by this base. So that will give me Wx divided by L minus X equals to W divided by L that gives me Wx equals to WL minus X divided by L. Now because we have cut our section at XX, there will be reactions at the point where we cut. There will be a shear force. The positive shear force will be upward and positive bending moment will be clockwise, that is M and V. Now let's write the moment equation about the section. Sigma M about X will be 0 and I'll consider clockwise moments positive. So this gives me moment because of V will be 0 because it passes through the section. M will be a positive moment. M, the resultant force because of the triangular load, will be half height into base and its point of application will be 1/3 from the right angle corner of the triangle. So this will be the resultant force and this distance will be L minus X by 3 and the moment because of this will be clockwise. So plus half Wx into L minus X, that is force, into lever arm, that is L minus X by 3. The moment because of RB will be anti-clockwise. So minus RB into lever arm, that is L minus X, equals to 0. This gives me M equals to RB L minus X minus half Wx into L minus X squared divided by 3. I can substitute values of RB and Wx. RB is WL by 6. So this gives me M equals to WL by 6 L minus X minus half Wx is WL minus X and L minus X square gives me cube divided by 3 L. Or I can write this as WL by 6 L minus X minus W by 6L L minus X cube. So this is my variation of bending moment along the length of this corresponding simply supported beam. Now next step is to draw the analogous column. Analogous column will be a short column with width L and breadth 1 upon EI. So let's say this is the cross section, this is width L and breadth will be 1 upon EI and this is cross section or top view. The side view will be short height and width L. On this short column we will apply the loading equals to mx upon EI and m we have just got as WL by 6 L minus X minus W by 6 L L minus X cube and this will be a parabolic loading. So I will apply some parabolic loading. Now pressure at the base of column because of this loading can be written as P equals to F by A plus minus M dash divided by I dash into X. F is the total force because of loading on analogous column. A is area of cross section. M dash is moment because of the loading on analogous column about the centroidal axis of column cross section, and because we have a rectangular cross section, the centroid will be middle of the cross section. I dash is second moment of area of analogous column cross section about centroidal axis, and X is the distance of any point on column cross section from centroidal axis. And here this edge is A, this edge is B, this point A, this point B. Now let's find all these quantities. F will be area under this load that I can find by integrating from 0 to L mx upon EI dx. So let's move to next slide and I'll evaluate this integral. So f equals to integral 0 to L, mx is wl by 6 L minus x minus w by 6L L minus x cube dx, and 1 upon ei I will take out. This will be equals to 1 upon ei, and now I'll integrate wl by 6 into L minus x squared by 2, and there will be a minus sign because there is a minus before x, minus w by 6L L minus x to the power 4 by 4, and because there is minus sign before x, I'll get a minus sign out. So this minus minus will become plus, and limit from 0 to L, that is equals to 1 upon ei. When x equals to L, this will become 0 and this will also become 0. So I'll have 0 minus, at x equals to 0, the first term will become minus wl by 6 into L squared by 2, plus second term will become w by 6L L to the power 4 by 4. Here L will cancel L to the power 4 to give L cube. This simplifies to 1 upon ei, the minus sign, minus wl cube by 12 plus wl cube by 24. This becomes equals to 1 upon ei minus, and these two terms will add up to give minus wl cube by 24, and here this minus minus will become plus. So this gives me f equals to wl cube divided by 24 ei. Area of the cross section, that is straightforward, that will be L into 1 upon ei, that is L by ei. Next I'll write I dash. I dash is second moment of area about centroidal axis, and that is width into depth cube by 12. Width is dimension parallel to the centroidal axis and depth is dimension perpendicular to the centroidal axis. So that gives me 1 upon ei L cube divided by 12, that is L cube divided by 12 ei. And next is m dash. M dash will be moment because of distributed load about centroidal axis, and that point will be here, which is midpoint of the width. To find m dash, I'll take a strip at a distance x from point A with width dx. Force because of this strip will be mx upon ei into dx, and the lever arm for this will be this distance, which is L by 2 minus x. So m dash will be integral from 0 to L mx upon ei dx, that is force because of this small strip, into lever arm, that is L by 2 minus x, and this moment will be in anti-clockwise sense. This I can evaluate as m dash equals to integral from 0 to L 1 upon ei wl by 6 L minus x minus w by 6L L minus x cube into, and here for L by 2 minus x I can take 2 LCM, so I get L minus 2x by 2 dx. Now from this integral I can take 1 upon ei out of the integral, w by 6 also out of the integral, and this 2 also out of the integral. So I get w divided by 12 ei integral 0 to L into L minus x into L minus 2x minus L minus x cube into L minus 2x divided by L dx. Now here I'll multiply these two factors and integrate, but it will be little tedious to multiply these two. So I will integrate the second part by using integration by parts. So that will give me equals to w by 12 ei integral 0 to L into L squared minus 3Lx plus 2x squared dx minus 1 upon L integral 0 to L, and I will make this first function and this one second function. So I write them L minus 2x L minus x cube dx equals w by 12 ei. The integration for this will be this L as it is, L squared x minus 3L x squared by 2 plus 2x cube by 3, limit from 0 to L. This integral I will evaluate separately. Let's write it down. Integral 0 to L minus 2x L minus x cube dx. This will be first function as it is, that is L minus 2x, integral of second function, that is L minus x to the power 4 divided by 4 and a minus sign because I have a minus here, and the limit from 0 to L minus integral 0 to L derivative of first function. So that gives me minus 2 integral of second function. So that gives me L minus x to the power 4 divided by 4 and a minus sign because there is a minus here, dx equals to, here when I put limits at x equals to L, this expression becomes 0. So I get 0 minus, when x equals to 0, I get L into L to the power 4 divided by minus 4 minus, and here this minus becomes plus, and also this 2 cancels this 4 by 2. So I get 1 by 2 L minus x to the power 5 divided by 5 and a minus sign because I have minus here, and the limit from 0 to L. This gives me here this minus plus. So I get L to the power 5 by 4 minus, again here this minus plus 1 by 10. At x equals to L, this becomes 0, and at x equals to 0 it becomes minus L to the power 5, that is equals to L to the power 5 by 4 minus L to the power 5 by 10 equals to, and I can take 20 LCM. So I get 5 L to the power 5 minus 2 L to the power 5 equals to 3 L to the power 5 by 20. This I can substitute back. So I get minus 1 by L, 3 L to the power 5 by 20, and here this L will cancel L to the power 5 to give me L to the power 4, and here when I substitute limits in this expression at x equals to L, I get w divided by 12 ei L at x equals to L, L cube minus 3L cube by 2 plus 2L cube by 3, and at x equals to 0, this whole thing becomes 0 minus 3L to the power 4 by 20. This whole thing simplifies to give me L cube by 6. So I get equals to w divided by 12 ei into L cube by 6 minus 3L to the power 4 by 20, that is equals to w by 12 EI to L to the power 4 by 6 minus 3L to the power 4 by 20 to W by 12 EI. Take 60 as LCM, then I am left with 10 L to the power 4 minus 9 L to the power 4. This gives me W L to the power 4 divided by 720 EI. So this is my M dash. So M dash is W L to the power 4 divided by 720 EI, and that is in anti-clockwise sense. So now XA is this, and that is L by 2, and this distance will be XB, and XB is also L by 2. So now I can write pressure at both the edges for this column, and also note that because the resultant moment about centroidal axis because of this distributed load is anti-clockwise, that moment will have a tendency to rotate our column in this way. So moment M dash will produce tensile stress at A and compressive stress at B. So for PA I will use plus sign, and for PB I will use minus sign. So PA becomes F by A plus M dash by I dash XA, that is equals to WL cube divided by 24 EI divided by L by EI plus M dash is WL to the power 4 divided by 720 EI divided by L cube divided by 12 EI into XA is L by 2. So that will be equals to, here I can cancel this EI with this EI, this L with this L cube to give me L squared, this EI with this EI, this 12 with this 720 to give me 60, this L cube with this L4 to give me L. So I am left with WL squared by 24 plus WL by 60 into L by 2, that is equals to WL squared by 24 plus WL squared by 120. This you can simplify by taking LCM 120. This gives me 5 plus 1 WL squared, that is equals to 6 WL squared by 120, and here this 6 will cancel this 120 to give me 20. So that is WL squared by 20, that is equals to M AB, and PB will have minus sign. So PB I can write as F by A minus M dash by I dash X B, that will be equals to this. I can simplify again, that is equals to, so that is equals to WL squared by 30, that is equals to M BA.